we're going to continue our conversation about our star, the sun, and look a little bit about how we interact with the sun in the form of, for one thing, solar weather. All right, so we have different types of solar activity, and we've talked in the past about particles from the sun streaming towards the earth and the fact that we have a magnetosphere and how that protects us. But we have a lot of solar activity going on, and it's really always a challenge to learn about that and how we got there and then how it actually interacts with us on Earth. All right, so the solar activity that we look at, we often hear referred to as solar weather. And for lack of a better term, it's just something that we can relate to. We understand Earth weather, and we understand how it changes and how it can be influenced by other things. And so, in effect, that's what the sun's doing. We're interacting with the sun in kind of a different way. It changes over time, it has its different seasons and cycles, and it doesn't always interact with us. We can watch it happen in other places as well. So, some of the things on the sun that help us learn about solar activity and solar weather are sunspots. We had to figure out why they were caused and what was going on there. Solar flares and solar prominences. We see those on the edges of the sun. They're often facing us. It's very hard to see them when they're facing us. But all of these different solar phenomena are related to the magnetic fields. All right, so let's take a look at sunspots. So just a quick recap on magnetic fields. When we remember the Earth has its core, and then it has an outer core, and it is spinning, and it's metallic, and it creates a magnetic field. And so we have a magnetic pole north-south. But when we are talking about the sun, this is a completely different beast. It does not turn together as a single unit. It's a giant ball of gas with different densities. So it's going to have different rotational rates across its from the equator up to the poles. And so that's going to create very, very, very different magnetic interactions than we're used to. These particular objects are sunspots. We pointed them out in the lecture previous to this. And if you remember when we talked about eclipses, lunar and solar eclipses, and the shadows that a sphere makes, we use two words. We use an umbra and a penumbra. And we're going to use the same thing here because we do have a darkest part of a sunspot and then this fading part on the outside. So we use the same terms, so the umbra and the penumbra as well. So if you remember, the surface of the sun in general is about 6,000 Kelvin. And when we get to this sunspot, we've dropped 2,000 degree Kelvin here. And so it is much, much cooler. And since it's cooler, it appears to our eyes to be darker, right? So then this just happens to be the cool spot. So then if these are all little convection cells, what's going on that would cause the convection to break and these cooled off areas not to get pulled back down again through the convection zone where it can get reheated up again by the radiative zone. So we've kind of got a broken convection system. And what we've learned over time is it's due to magnetic fields. So some of the things that helped us determine this is we are looking at spectral lines of the sun. So remember, those are the lines that kind of show us the different elements that are in there. We use them for different purposes. To determine composition. We can also use them to determine movement away and towards from us. However, we get these spectral lines and then we get a blurring and a splitting of them, and then they come back and be into a normal state again. And what we determine in the lab is that really very strong magnetic fields can change what the spectral lines look like. So when we started applying that concept to other things, and this other stars were hard to see at first, but our sun being fairly close, it was kind of easy to see that. So we could see those splitting of lines, and so we knew there was something magnetic in that. So if we think again about magnetic field lines, and the fact that we have magnetic field lines and we have them near the surface of the sun, so we have all these charged particles. The charged particles are going to follow the magnetic lines. The closer they are together, the stronger the magnetic lines are. The further apart, the weaker. And then the directionality of them help determine on Earth which way the magnet, a compass magnet, would point. And so kind of here we have this little illustration, and we've got these charged particles flowing along these lines. So then what we have going on here on the sun, and you can see these giant loops. So we have these giant magnetic field lines And these prominences streaming out, and they're beginning and ending on the things that end up being the sunspots. So what is going on with the sunspots is we have this north and south magnetic poles and the charges and those charge lines that are running between them, pulling all of the material from the sun along the loop lines. So they're basically spiraling along those loop lines. So very, very tightly wound magnetic fields. And so as they run back and forth between these sunspots, they're also disrupting what's going on in the convection below them, which is why those dots can kind of fan out to the point where they're very, very dark because they've cooled off quite a bit here at the part where it's most broken, for lack of a better word. And then as it moves away, it starts to warm up because then the unbroken convection around them is going to slowly kind of tear apart at those edges. All right, so here we have, if you can imagine, these long magnetic field lines going from point to point. We're looking at X-ray here, so remember using our very different ways of looking at light. So this is, we're blind to X-ray, and remember we're blind to most light. We can only see invisible light where we're blind to everything else. So we have developed ways to see X-rays with other telescopes. And so you can see all of the loop lines here. Now what happens is if these loops tend to cross and you've got a loop out here of material, it breaks off and it actually gets pushed out away from the sun. And so you can have those flares or coronal, these flares in this case, get pushed out into space. Here's one as well. And so this is a really, really large prominence moving up. And again, just imagine the magnetic field lines moving from point to point. They're absolutely beautiful to look at a telescope. If you ever get an opportunity to see, to look at the sun through a hydrogen alpha telescope, it's a special telescope, and that's all it does is look at the sun in this wavelength. Definitely get the chance to do that because it's really beautiful to watch these. And just for kind of a point of reference, this is the Earth to scale to this magnetic line and drawing this prominence off. Okay, so this is a real picture, not an imaginary one and not an artist's conception. All right, so then when we look at it in different wavelengths, when we look at it in X-ray, which is going to be our higher energy wavelength, we can see the higher energy and therefore higher temperature that we have all around this corona and all through the chromosphere here, all touching down in the photosphere. So, and I've learned from previous things, I wish I could go ahead and play this for you, but what we've noticed that when we have Panopto try and play a movie for you, it gets jumpy and you miss quick transitions. So this movie from NASA Goddard is out in the module, and I really want you to watch it. But here's what you're looking at. So this is close to visible light range of the sun, the orange ball, and you can see the little sunspots right here, and there's some more hidden behind here. Each one of these colors represents a different wavelength of light. So these are all the wavelengths that are we're blind to, but each one is going to be looking at a different energy level. And so as it passes over the sunspots, in some cases you can't see them because we're looking at a higher level of the sun. But in some cases, when you're looking at the energy of the prominences or magnetic field lines pulling material out over it, you'll catch that. So don't skip this part. Go ahead and go watch it when we get to the end of this section. All right, so that's great. So how does it affect humans? So this is the SOHO Space Telescope, and so this disc right here is a mask. If you've ever been out and it's been bright and you've been trying to look up at the sun, look up at the sky at something close to the sun, you'll put your hand up, right, to mask the sun so that you can see the stuff around it. That's what this space telescope does. It has a little masking arm that sticks out. So this white disc would be the edges of the sun. This is the mask. And so what you're looking at right here is a huge solar flare coming off of the edge of the sun. And so this, once it releases and pushes off, will be called a coronal mass ejection, and it's sending all of that, those charged particles and all of the material from the sun off into space. And those are the things that can really just really cause a lot of problems on Earth. So when that happens, again, they come streaming towards us from the sun. And fortunately for Earth, we have a large magnetosphere, and this front edge, the kind of the bow of what's going on, ends up getting compressed as all of the material comes streaming by, but our own magnetic field lines end up getting excited, and you end up getting charged particles spiraling around that, and then they interact with all of the chemicals in our atmosphere, all of the naturally and not so natural elements of our atmosphere, and that's when we get the aurora borealis in the north and australis in the south. But the other thing that they can do, because they are ionizing those elements in our upper atmosphere, is if you think of everything that's between the Earth's surface, its atmosphere, and high orbit around us, we've got communication satellites up there. We've got a space station up there with people living on it. So all of that information and all of those things up there have to be prepared to deal with this type of space weather. We've had instances where power grids have been knocked out because of solar flares. We've had unplugged telegraph lines continue to send messages based on the electrical energy in the atmosphere instead of a power source. So there's kind of a lot of interaction between the sun and the surface of the Earth, even with our protective atmosphere and even with our protected magnetic field. So we mentioned earlier the fact that the sun has its own activity cycles, and the sunspot cycle is probably the one that is kind of the easiest to recognize, and that's an 11-year cycle. So we go through things called solar min and solar max, and it is when we have lots and lots of sunspots on the sun, we have solar maximum, and we have very little of them, we have solar minimum. And so this kind of shows a particular graph of that sunspot cycle. All right, so we talked about the magnetic field lines, and we talked about earlier the fact that since the sun is a ball of gas, that we're actually going to have different rotations based on where you are. So if you can think about the fact here on the far left, when we have magnetic field lines, and so if it was the Earth and this was rotating, we would have the axis, and we would have kind of everything rotating together as a unit. But with the sun, considering the fact that the equator is moving much, much faster than the poles are, these magnetic field lines end up getting wrapped around tighter and tighter and tighter, and so that's why you get sets and sets and sets of these little north-south, north-south, north-south pairings, because it is the folding over of all of these magnetic field lines. Okay, so that is our little lecture on space weather and different space cycles and how they interact. So go back out into the module, watch the little videos, and then we will catch you up on kind of analyzing the starlight.